Running an isolated ground conductor within metal conduit presents potential problems, even if the design prevents bonding the insulated wire to the conduit. The primary concern is that the metal conduit will behave as an antenna, effectively capturing electromagnetic interference or electrical noise from the surrounding environment. This captured noise can then be conducted onto the isolated ground conductor, potentially interfering with the operation of the delta-V control panel. The fundamental principle at play here is electromagnetic induction. When electrical equipment operates nearby, it generates electromagnetic fields. These fields can induce currents in conductive materials, such as the metal conduit. If the isolated ground conductor is run within this conduit, it becomes susceptible to picking up these induced currents, which manifest as noise. To mitigate this issue, several alternative approaches should be considered. Firstly, utilize the non-metallic conduit. Non-metallic conduits, such as polyvinyl chloride or PVC, do not conduct electricity and therefore cannot act as an antenna. This prevents the induction of noise currents onto the isolated ground conductor. Secondly, implement a dedicated raceway system. This involves running the isolated ground conductor in a completely separate conduit system that is physically and electrically isolated from the conduit system used for the 120-volt UPS power. This separation minimizes the potential for noise coupling between the two systems. Thirdly, maintain physical separation from noise sources. The isolated ground conductor should be routed as far as practically possible from potential sources of electrical noise such as transformers, motors, variable frequency drives, and other electrical equipment. These devices are notorious for generating significant electromagnetic interference. Fourthly, consider shielded cable. Using shielded cable for the isolated ground conductor can provide an additional layer of protection against noise. The shield should be properly grounded at one end only, typically at the source, to prevent ground loops. Fifthly, implement proper grounding techniques. Ensure that all grounding connections are made properly and are low impedance. Loose or corroded connections can introduce noise and degrade the effectiveness of the grounding system. Sixthly, utilize filtering techniques. Employing filters at the delta-V control panel can help to attenuate any noise that may be present on the isolated ground conductor. These filters are designed to block high-frequency noise while allowing the desired signal to pass through. Seventhly, perform thorough testing and verification. After implementing any changes to the grounding system, it is essential to perform thorough testing to verify that the noise levels have been reduced and that the delta-V control panel is operating correctly. This may involve using a spectrum analyzer or other specialized equipment to measure noise levels. Ground loops are a significant concern in electrical systems, and they can be particularly problematic in sensitive electronic equipment. A ground loop occurs when there are multiple paths to ground, creating a loop that can induce circulating currents. These circulating currents can introduce noise and interfere with the operation of equipment. Isolated ground systems are specifically designed to prevent ground loops by providing a single, dedicated path to ground for sensitive equipment. However, if the isolated ground conductor is run in metal conduit, the conduit can inadvertently create a ground loop. The National Electrical Code, or NEC, provides guidelines for grounding and bonding electrical systems. While the NEC does not specifically address isolated ground systems in detail, it does provide general requirements for grounding and bonding that are relevant. For example, NEC section 250.96 addresses the bonding of metal enclosures. This section requires that metal enclosures containing electrical conductors be bonded together to form an electrically continuous path. This bonding helps to prevent voltage differences between enclosures, which can be a source of noise. NEC section 250.146 addresses the use of isolated ground receptacles. This section permits the use of isolated ground receptacles under certain conditions, but it also requires that the grounding conductor for the receptacle be insulated from the metal box in which it is installed. The purpose of this requirement is to prevent the metal box from becoming a source of noise. Understanding the principles of electromagnetic compatibility, or EMC, is crucial in designing and maintaining effective isolated ground systems. EMC is the ability of electrical equipment to operate without causing or being susceptible to electromagnetic interference. EMC design principles involve minimizing the generation, transmission, and reception of electromagnetic interference. This can be achieved through proper grounding, shielding, filtering, and cable routing techniques. The length of the isolated ground conductor can also affect its susceptibility to noise. Longer conductors are more likely to pick up noise than shorter conductors. Therefore, it is important to keep the isolated ground conductor as short as possible. The gauge of the isolated ground conductor should be sized appropriately to handle the expected fault current. The NEC provides guidelines for sizing grounding conductors in Table 250.122. It is important to consult this table to ensure that the conductor is adequately sized. The type of insulation used in the isolated ground conductor can also affect its performance. Some types of insulation are more effective at blocking noise than others. Therefore, it is important to select an insulation material that is appropriate for the application. When installing an isolated ground system, it is important to follow the manufacturer's instructions carefully. The manufacturer's instructions will provide specific guidance on how to install the system correctly and how to avoid common problems. Regular maintenance and inspection of the isolated ground system are essential to ensure that it continues to function properly. This includes checking the grounding connections for looseness or corrosion, inspecting the conductors for damage, and testing the system for noise. In summary, running an isolated ground conductor in metal conduit can introduce electrical noise and interfere with the operation of sensitive equipment. To avoid this problem, use non-metallic conduit or separate raceway, maintain physical separation from noise sources, use shielded cable, implement proper grounding techniques, utilize filtering techniques, and perform thorough testing and verification. Always follow the manufacturer's instructions and consult the NEC for guidance on grounding and bonding electrical systems. When dealing with sensitive electronic equipment like the Delta V control panel, maintaining a clean and stable ground reference is paramount. The isolated ground system is intended to achieve this, but improper installation can easily negate its benefits. Firstly, let's delve deeper into the intent effect of metal conduit. Imagine the conduit as a long, hollow tube. This tube is highly conductive, making it an efficient receiver of electromagnetic waves. These waves are generated by countless sources in the environment, from nearby electrical equipment to radio transmissions. The conduit intercepts these waves, and the energy is converted into electrical currents flowing within the conduit walls. These currents, in turn, can induce voltages in the isolated ground conductor running inside. The induced voltage is manifest as unwanted noise signals superimposed on the clean ground reference. Secondly, consider the concept of impedance. Impedance is the opposition to the flow of alternating current. Every conductor, including the isolated ground wire and the metal conduit, has some amount of impedance. The impedance of the isolated ground wire should be kept as low as possible to provide a direct path for fault currents back to the source. However, the impedance of the metal conduit can vary depending on factors such as its length, diameter, and the presence of any breaks or discontinuities in its construction. High impedance in the conduit can hinder its ability to effectively shield the isolated ground wire from noise. Thirdly, ground loops deserve special attention. A ground loop occurs when there are multiple paths to ground, creating a closed circuit. This circuit can act like an antenna, picking up electromagnetic noise and circulating it throughout the grounding system. The isolated ground system is designed to prevent ground loops by providing a single, dedicated path to ground. However, if the metal conduit is inadvertently connected to other grounded objects, such as building steel or other equipment enclosures, it can create a ground loop. Fourthly, let's explore the role of shielding. Shielding involves enclosing a conductor or piece of equipment in a conductive barrier to block electromagnetic interference. Shielded cables are commonly used to protect sensitive signal wires from noise. The shield is typically made of braided wire or metallic foil and is connected to ground at one end. When used properly, shielded cables can significantly reduce the amount of noise that is coupled onto the signal wires. Fifthly, Filtering is another powerful technique for reducing noise. Filters are circuits that are designed to block certain frequencies while allowing others to pass through. Filters can be used to remove unwanted noise signals from the isolated ground conductor. There are many different types of filters available, each with its own characteristics and applications. Sixthly, proper bonding is essential for creating a low impedance ground path. Bonding involves connecting together all of the metal parts of the electrical system, such as conduit, enclosures, and equipment frames. This creates an electrically continuous path that helps to equalize voltage potentials and reduce the risk of electric shock. Bonding is typically accomplished by using bonding jumpers, which are short lengths of wire that connect the metal parts together. Seventhly, consider the impact of harmonics. Harmonics are multiples of the fundamental frequency of the power system. For example, in a 60 Hz system, the second harmonic is 120 Hz, the third harmonic is 180 Hz, and so on. Harmonics can be generated by nonlinear loads such as electronic equipment and variable frequency drives. Harmonics can cause a variety of problems, including overheating of equipment, increased energy consumption, and interference with sensitive electronic equipment. Eighthly, surge protection is another important aspect of protecting sensitive equipment from damage. Surges are transient overvoltages that can occur on the power system due to lightning strikes, switching operations, or other events. Surges can damage or destroy electronic equipment if they are not properly suppressed. Surge protective devices, or SPDs, are designed to protect equipment from surges by diverting the surge current to ground. Ninthly, let's discuss the importance of regular inspections and maintenance. Grounding systems should be inspected regularly to ensure that they are functioning properly. This includes checking for loose connections, corrosion, and damage to conductors. Any problems that are found should be corrected promptly. Tenthly, compliance with the National Electrical Code, or NEC, is essential for ensuring the safety and reliability of electrical systems. The NEC provides detailed requirements for grounding and bonding, as well as for the installation of electrical equipment. It is important to consult the NEC when designing and installing an isolated ground system. Let's expand on NEC requirements related to grounding and bonding. NEC Article 250 covers grounding and bonding in detail. This article provides requirements for grounding electrode systems, grounding conductors equipment, grounding conductors, and bonding. Section 250.4 provides general requirements for grounding and bonding, emphasizing the need to create a lower impedance path for fault current to facilitate the operation of overcurrent protective devices. Section 250.24 covers grounding service applied alternating current systems. This section requires that the grounded conductor be connected to a grounding electrode system. Section 250.50 covers grounding electrode systems, specifying the types of electrodes that are permitted, such as metal underground water pipes, metal frames of buildings, and ground rods. Section 250.92 covers bonding of metal enclosures, requiring that metal enclosures containing service conductors be bonded together. Section 250.96 covers bonding other enclosures, requiring that metal enclosures containing other than service conductors be bonded together. Section 250.118 specifies the types of equipment grounding conductors that are permitted, such as wire, cable, and metal conduit. Section 250.122 provides requirements for sizing equipment grounding conductors. The size of the equipment grounding conductor is typically based on the size of the overcurrent protective device protecting the circuit. Now let's discuss some practical considerations for installing an isolated ground system. Firstly, choose the right location for the isolated ground panel. The panel should be located as close as possible to the equipment that it is serving to minimize the length of the isolated ground conductor. Secondly, use a dedicated conduit system for the isolated ground conductor. This will help to prevent noise from being coupled onto the conductor. Thirdly, use shielded cable for the isolated ground conductor. This will provide an additional layer of protection against noise. Fourthly, properly terminate the shield of the shielded cable. The shield should be grounded at one end only, typically at the source. Fifthly, use a high-quality grounding electrode. The grounding electrode should be made of copper or copper-clad steel and should be driven deep enough into the ground to reach moist soil. Sixthly, use a low-impedance grounding connection. The grounding connection should be made using a crimped or welded connection. Seventhly, test the isolated ground system after it is installed. The system should be tested to ensure that it is functioning properly and that there is no noise in the isolated ground conductor. In addition to the above considerations, it is also important to be aware of the potential for common mode noise. Common mode noise is noise that is present on both the hot and neutral conductors of a circuit. Common mode noise can be difficult to filter out because it is not easily distinguishable from the desired signal. One way to reduce common mode noise is to use a balanced circuit. In a balanced circuit, the hot and neutral conductors are twisted together to cancel out any noise that is common to both conductors. Another way to reduce common mode noise is to use a common mode choke. A common mode choke is a filter that blocks common mode noise while allowing differential mode noise to pass through. Let's also consider specific issues related to the Delta V control panel. The Delta V control panel is a sophisticated piece of electronic equipment that is sensitive to noise. It is important to protect the panel from noise to ensure that it operates reliably. Firstly, ensure that the panel is properly grounded. The panel should be connected to the isolated ground system using a dedicated grounding conductor. Secondly, use shielded cables for all of the input and output signals to the panel. This will help to protect the signals from noise. Thirdly, install surge protection at the panel. This will protect the panel from damage due to surges. Fourthly, filter the power supply to the panel. This will help to remove any noise that may be present on the power line. Fifthly, locate the panel away from sources of noise. Avoid locating the panel near transformers, motors, or other electrical equipment that can generate noise. Remember that careful planning and attention to detail are essential for designing and installing an effective isolated ground system. By following the guidelines outlined above, it is possible to minimize the risk of noise and ensure that sensitive electronic equipment operates reliably. Furthermore, if after implementing the above recommendations and you are still facing issues, it might be helpful to employ a power quality analyzer. These devices can help pinpoint the source of the disturbance by analyzing harmonic distortion, transient events, and voltage fluctuations. Remember that electricity is not always what we assume, and testing is the only way to prove any theory.